Welcome to the second video of Lecture 8 of Experimental Vibration Analysis. In this lecture, we discuss sensors used for vibration measurements. The content of this video is found in Chapter 7 of the book Noise and Vibration Analysis. In this video, we will discuss some of the most common sensors for vibration measurements. We will restrict the discussion to piezoelectric sensors, since those are by far the most common sensors. And we will thus present the accelerometer, the force sensor, impedance heads, and impulse hammers. Before describing the different sensor types, we needed to describe the piezoelectric effect and some common technologies shared by all piezoelectric sensor types. The piezoelectric effect is a physical property that some materials, particularly quartz crystals, exhibit. The effect is that charges are polarized over the crystal when a force is applied. Typical piezoelectric crystals are very stiff, which makes them suitable for sensors. The effect is also linear over a vast dynamic range. An additional advantage is that the effect is self-generating, so no outside power is needed. However, since charge cannot be measured, piezoelectric sensors are limited to measure change in charge, which means that we're limited to measuring dynamic signals. Some of the sensor types that can be built using piezoelectric sensors are sensors for measuring pressure, force, acceleration, and sound pressure. When a piezoelectric sensor is used, the charge output needs to be converted to a voltage that can be compared or that can be measured by the measurement system. In the old days, and sometimes still today, that is accomplished by connecting the sensor through a cable to a charge amplifier, as indicated here. An important property of charge amplifiers is that the output voltage is, to a good approximation, only proportional to the charge we want to measure, divided by the capacitor value, C sub F, from the feedback capacitor of the operational amplifier, as indicated in the figure. This has two important consequences. First, that the amplification is independent on the capacitance of the sensor and cable. And secondly, since capacitors come in a large variety of values, from picofarads to millifarads, it's easy to design charge amplifiers with adjustable gain over very large ranges. It's not uncommon with amplification from 1 to 10,000 times in a charge amplifier. This means that the same sensor can be used to measure very low vibration levels in one application and very high vibration levels in a different application. There are, however, some drawbacks with using charge amplifiers and charge mode sensors. The measurement quality is not as good as is possible with the other type of sensor which is common today, the IEPE sensor that we will soon describe. On the other hand, charge mode sensors are common for very high temperature sensors, for example. The sensor type most common today is the IEPE sensor, the Integrated Electronic Piezoelectric Sensor. This is a sensor type with built-in electronics that perform very well at a much lower cost than charge mode sensors. In the figure here, we see the sensor with its built-in amplifier on the left-hand side. The cable is described by a capacitance. And on the right-hand side, there is a circuit producing a current for powering the amplifier in the sensor and a decoupling capacitor that removes the DC voltage from the output voltage. The technique works as follows. The current source produces a constant DC current. This current opens up the amplifier and a DC voltage of approximately 10 volts is produced over the sensor. The sensor output, U sub A, is then producing a variation in this DC voltage, which on the other side of the decoupling capacitor, U out here, is seen as a pure AC signal. There are three important properties of the IEPE standard that you should be aware of as a user. First, the full-scale voltage of the sensor is ± 5 volts. This voltage is a variation on the DC bias voltage, as indicated in the plot here, although the measurement system sees it as a ± 5 volt signal because the DC is removed in the AC coupling. Second, the compliance voltage is the voltage used to provide the current for the sensor. This voltage is specified as 18 to 30 volts by the standard, but there are sensors who are specified to a higher compliance voltage, so you should check that your measurement hardware is compatible with your sensor. If the compliance voltage is too low to support the DC bias voltage, plus the 5 volt sensor output, plus any possible common mode voltage felt by your measurement system, clipping could occur. Third, the current excitation needs to be between 2 and 20 milliamps. It is also important to note that if you have long cables, you may need more than the minimum current specification. Also, you should be aware that many measurement systems, typically those powered by USB, with built-in supply for IEP sensors, are supplying only 2 milliamps to minimize power consumption. Some sensors also require more than 2 milliamps to work properly. So again, you should check that your measurement hardware and your sensors work together. For historic reasons, various manufacturers have different names for the IEPE standard. The names shown in the table here, from some of the larger manufacturers, all stand for IEPE sensors. And with the exceptions mentioned above for the requirements for minimum current supply and compliance voltage for some sensors, these all stand for the same sensor technology. Many sensors for noise and vibration measurements can be obtained in a TEDS version today. TEDS stands for Transducer Electronic Datasheet and is a standard standardized by IEEE. If a sensor is containing TEDS, it has a built-in EEPROM, an electronic memory, with information about the sensor, manufacturer, product name, etc., the type of sensor, and most importantly, the sensitivity of the sensor. This allows the measurement system to automatically obtain this information and therefore removes the risk of mistakenly enter the wrong measurement sensitivity into the measurement system, which is always present, that risk that is, if you need to manually fill in these factors. TED sensors can be strongly recommended. Now, the upper frequency of any vibration sensor is usually determined by mechanical properties that we will describe later. It can also be affected by long cables, as I talk about in the book. The low frequency performance, however, is determined by a combination of the sensor and the current supply, which both acts as high-pass filters. As we recall from chapter 3, a high-pass filter can be characterized by its time constant. And thus we have two time constants in series, the sensor followed by the current supply. The effect of two time constants in series is found by the following formula. 1 over the combined time constant is the sum of 1 over each of the time constants, similar to how you compute springs in series. Thus, if the time constant are more than a factor 10 in difference or so, the smaller time constant determines the sum. The effective cutoff frequency we obtain is thus f sub c approximately equal to 0.16 divided by the combined time constant tau. The frequency response may look similar to this, where the frequency axis is normalized to the cutoff frequency. You should be particularly aware that this means that if the cutoff frequency is, for example, 1 Hz, which is common, then for an accuracy of 5%, you need to be above 3 Hz. Now that you understand the principles of piezoelectric sensors, and particularly the IEPE sensors, it's time to describe the most common sensors for mechanical vibration measurements. We start by the accelerometer. The piezoelectric accelerometer is by far the most common transducer for vibration measurements. This is partly due to its small size and low weight, but also because it has a very long term stability. And also it has a low noise level as well as a large dynamic range. And it has a large frequency range over which it can operate. The simplest principle of accelerometer design is shown here. The sensor consists of a stiff base to which the piezoelectric crystal is attached, and above the piezoelectric crystal a seismic mass is mounted. Although not shown in the figure here, for simplicity, the crystal is statically pre-compressed by springs, so that the sensor also works for an acceleration directed downwards. When the sensor is accelerated upwards, the seismic mass will act on the crystal with its inertia, and the crystal will be compressed by a force of the seismic mass times the acceleration. The output of the sensor is thus a charge proportional to the acceleration. The sensitivity tells the number of picocoulombs per acceleration unit. For example, as shown here, picocoulombs per G. Now, for an IEPE sensor, the output will be a voltage, and the sensitivity will of course be in millivolts per G. The accelerometer is based on the seismic mass on top of the crystal. This forms an S-stop system with the stiffness of the crystal, and thus the accelerometer will obviously have a resonance. The frequency of this resonance is called the accelerometer's mounted resonance frequency, often denoted as here by F sub m. To have a small phase error, the resonance must have little damping, so the output of the sensor is approximately the theoretical output divided by 1 minus the ratio of F and F sub m squared. Thus, for a 10% accuracy, the sensor can be used up to approximately a third of the mounted resonance frequency. Sometimes a fourth of the frequency F sub m is used instead, giving 5% accuracy. You should note, however, that these frequencies are theoretical. Once the sensor is mounted in a non-stiff point, it will have a different behavior. Now, the simple design principle we showed above is called a compression mode accelerometer. This is a common design in the most inexpensive accelerometers due to its simple design. This design has some drawbacks, however, the main being its high sensitivity to bending of the base plate, which often occurs when the sensor is mounted on a flexible vibrating surface. The design is also sensitive to temperature changes. A better design, although also more expensive, is the shear mode design. In this sensor, the seismic mass acts by a shear force on the crystal, which is standing up as indicated here. This gives it a higher sensitivity per mass unit. And also, this design is much less sensitive to base bending and temperature changes. Also, the transverse sensitivity that we will define below is lower for this type of design. There are many ways to mount an accelerometer to the measurement object. The safest way is to screw the accelerometer by use of a stud. But this, of course, makes it necessary to drill and thread a hole in the measurement object. If this cannot be done, the accelerometer can be glued to the object. There are many types of glue used for this, such as cyanoacrylate glues, also called superglues, and hot glues. Another common way to mount accelerometers is by using wax. Wax is a very nice material to work with in the lab, provided that the temperature is not too high and that the vibration levels are reasonably small. Finally, accelerometers are often used with magnets. It should be stressed, though, that this mounting method should only be used for measurements on stiff structures, such as bearings, large structures, etc. Now, common to all mounting methods is that the surface must be flat so that the accelerometer does not rock. The surface must also be absolutely clean. Often you need to use some abrasive and clean the surface carefully. In this plot, you can see the frequency range achieved by mounting an accelerometer with different types of techniques. The measurements are normalized to yield the same result at 159 Hz. The two horizontal lines at 0.95 and 1.05 shows the ±5% deviation. As you can see, a thick layer of wax is crossing the line at approximately 1200 Hz, whereas the hot glue in this case crosses at approximately 3 kHz. You should note that this is an effect of both the specific accelerometer and of the thickness of the wax or glue. You should not take these actual numbers to apply in your own applications. Rather, you should make this measurement with your own sensors, and we will talk about how in a later slide in this video. If you want to learn how to properly mount accelerometers and how these results were produced, I recommend that you download the paper on lab exercises from my website. It describes some exercises that I recommend you to try if you're new to this field. When you want to select an accelerometer, there are many specifications to look for in the datasheet. Here, I've divided some of the important specifications into either operational or environmental factors. Most of these factors are described in more detail in the book. Otherwise, you should consult information from the manufacturer. The transverse sensitivity is an often overlooked parameter that I want to particularly stress. Also, I will show that it can sometimes cause unexpected problems. The transverse sensitivity is the output signal for an acceleration in a direction perpendicular to the measurement direction and related as a part of the output signal in the measurement direction. For example, 2% transverse sensitivity means that a 100 mV per G sensor excited by, say, 10 Gs in the transverse direction produces an output of 2% of 10 Gs times 100 mV per G, which equals 20 mV, compared to 1000 mV if the accelerometer had been mounted so that the actual vibration was in the measurement direction. Now, here is why the transverse sensitivity can be a problem if the structure has much different vibration levels in different directions. Assume that the structure has a vertical vibration level of 10 meters per square second and a horizontal vibration level of only 1 meter per square second. And we want to measure both simultaneously. Also assume a transverse sensitivity of 5%, which is a common number, although in the high end. Now, the output from the vertical sensor will be 10, the true level in the vertical direction, plus 5% of 1, the level in the transverse direction. This equals 10.05, which is of course fine. But now look at what happens with the output from the horizontal sensor. Its output will be 1, the actual vibration in the x direction, plus 5% of 10, the vibration in the transverse direction. This equals 1.5. So we have a 50% error. Thus, you should realize that in cases like this, you need to be really careful with the interpretation of your measurement signals. Now we will look at the force sensor. The force sensor is typically used in two places, either together with a shaker to produce a dynamic force input, or mounted on an impact hammer. The latter we will present later in this video. The principal design of a force sensor is very simple. The piezoelectric crystal is glued to a base, and another mass, called the mass above the force gauge, is glued to the other side of the crystal. Like for the accelerometer, the crystal is preloaded with a static force so it can measure forces in both directions. Here's a picture of an example force sensor. It's often not easy to see which side of the sensor that is supposed to be attached towards the structure. But it's very important to find this out, as the output force will otherwise be completely in error. Also, the mass above the force gauge is essentially added to the structure, producing a measurement error. Thus, for flexible points, it's important to keep this mass as small as possible. Force sensors are typically designed with very long time constants. This is so that they can be calibrated semi-statically. Force sensors are also very stiff, so the high frequency limit is entirely determined by the mounting. A large drawback with the force sensor is that it's very sensitive to transverse vibrations. This means that when used together with shaker excitation, we need to add a stinger, a flexible piece of wire or similar, between the shaker and the force sensor to remove any transverse forces. Here is an illustration from the paper presented earlier, showing an example of the connection of a stinger between the shaker on the left and the force sensor on the right. Note also that the force sensor shall always be attached to the structure, never on the shaker side of the stinger. Some specifications for force sensors are shown here. Of course, the maximum force level that can be measured is an important specification. Note that it may be different in the compressive and tensile directions because of the pre-tension springs in the sensor. Next, the mass above the force gauge is important since it's added to the structure and should be as light as possible. The time constant is, as said earlier, usually long, and it's not very important from a measurement point of view. And finally, the electric noise for IEPE force sensors may be an important specification to get as good dynamic range as possible. Sometimes a combined sensor called an impedance head is used. This is a sensor where a force sensor and an accelerometer are combined into one unit. The main advantage with an impedance head is that it's measuring the same point. So, whereas it can be difficult to position a force transducer and an accelerometer in the same point, which can be important for small objects where the modes have short wavelengths. Also, for flexible structures, it's possible to remove the effect of the mass above the force gauge from the frequency response measured by the impedance head. You can find more about that in the book. A drawback with impedance heads is, however, that they have a higher form factor, which means that they start to wobble at lower frequencies than a force sensor, which is more compact. The last sensor we will discuss is the impact hammer, illustrated here. sometimes also called impulse hammer. This is essentially a hammer shaft with a force sensor mounted onto a head. To add more weight to the head, a head expander can often be used. The force sensor typically comes with a number of tips of different hardness. By using these different tips, the length of the impulse and thus the spectrum of the force can be adjusted as shown here. The softer the tip, the lower the frequency range. The frequency range is, however, also dependent on the stiffness of the point which is excited. We will come back to the use of the impact hammer in a later lecture. A very important application that an impact hammer can be used for is so-called mass calibration. This is something you should make sure you have access to in your vibration lab, and you should use it often. Look in the paper I pointed you to before in this video to see more about how you use this. Typically, you mount an accelerometer on one side of a cylindrical mass that is accurately measured so you know its mass. You then excite it on the other side with an impact hammer. Essentially, the idea is that you measure the frequency response of acceleration over force. From Newton's second law, it follows directly that this frequency response should be a constant equal to 1 over the mass. This is thus independent of frequency. Thus you will obtain frequency responses such as ones shown here, that you recognized from before in this video. By using mass calibration, you can thus check that your accelerometer is working properly. You can also check that your method of mounting is within acceptable limits in your needed frequency range. And you can use it for actual calibration. This is recommended for the most accurate scaling of impact test measurements. This concludes the current lecture. Now you can go to the book and read the relevant chapter and work through the examples at the end of the chapter. Then you should also go to the chapter examples in the Accelerometer toolbox and read through these and run them and make sure that you understand all the steps involved. If you haven't yet downloaded the toolbox, you should do so at www.accelerometer.com. Welcome back to the next lecture when you have worked through this.